I'm Barton Poulson, and in this course, we're going to talk about data opus, or that's Latin for data needed. The idea here is that no data science, and that is a sad thing. So instead of leaving it at that, we're going to use this course to talk about methods for measuring and evaluating data, and methods for accessing existing data, and even methods for creating new custom data. Take those together, and it's a happy situation. At the same time, we'll do all of this still at an accessible, conceptual, and non-technical level, because the technical hands-on stuff will happen in later other courses. But for now, let's talk data. For data sourcing, the first thing we want to talk about is measurement. And within that category, we're going to talk about metrics. The idea here is that you actually need to know what your target is if you want to have a chance to hit it. There's a few particular reasons for this. First off, data science is action-oriented. The goal is to do something as opposed to simply understand something, which I say as an academic practitioner. Also, your goal needs to be explicit, and that's important because the goals can guide your effort. So you want to say exactly what you're trying to accomplish so you know when you get there. Also, goals exist for the benefit of the client because they can prevent frustration. They know what you're working on. They know what you have to do to get there. And finally, the goals and the metrics exist for the benefit of the analyst because they help you use your time well. You know when you're done, you know when you can move ahead with something. And that makes everything a little more efficient and a little more productive. Now, when we talk about this, the first thing you want to do is try to define success in your particular project or domain. Depending on where you are in commerce, that can include things like sales or click-through rates or new customers. In education, it can include scores on tests. It can include graduation rates or retention. In government, it can include things like housing and jobs. In research, it can include the ability to serve the people that you're trying to better understand. So whatever domain you're in, there will be different standards for success, and you're going to need to know what applies in your domain. Next are specific metrics or ways of measuring. Now, again, there are a few different categories here. There are business metrics. There are key performance indicators or KPIs. There are SMART goals. That's an acronym. And there's also the issue of having multiple goals. I'll talk about each of those for just a second now. First off, let's talk about business metrics. If you're in the commercial world, there are some common ways of measuring success. A very obvious one is sales revenue. Are you making more money? Are you moving the merchandise? Are you getting sales? Also, there's the issue of leads generated, new customers or new potential customers, because that then in turn is associated with future sales. There's also the issue of customer value or lifetime customer value. So you may have a small number of customers, but they all have a lot of revenue, and you can use that to really predict the overall profitability of your current system. And then there's churn rate, which has to do with losing and gaining new customers and having a lot of turnover. So any of these are potential ways of defining success and measuring it. These are potential metrics. There are others, but these are some really common ones. Now, I mentioned earlier something called a key performance indicator or KPI. KPIs come from David Parmenter, and he's got a few ways of describing them. He says a key performance indicator for business, number one, should be non-financial. So not just the bottom line, but something else that might be associated with it or that measures the overall productivity of the association. They should be timely, for instance, weekly, daily, or even constantly gathered information. They should have a CEO focus. So the senior management team are the ones who generally make the decisions that affect how the organization acts on the KPIs. They should be simple. So everybody in the organization, everybody knows what they are and knows what to do about them. They should be team-based, so teams can take joint responsibility for meeting each one of the KPIs. They should have significant impact. What that really means is they should affect more than one important outcome. So you can do profitability and market reach, or improved manufacturing time and fewer defects. And finally, an ideal KPI has a limited dark side. That means there's fewer possibilities for reinforcing the wrong behaviors and rewarding people for sort of exploiting the system. Next, there are SMART goals, where SMART stands for specific, measurable, assignable to a particular person, realistic, meaning you can actually do it with the resources you have at hand, and time bound, so you know when it can get done. So whenever you form a goal, you should try to assess it on each of these criteria. And that's a way of saying that this is a good goal to be used as a metric for the success of our organization. Now, the trick, however, is when you have multiple goals, multiple possible endpoints. And the reason that's difficult is because, well, it's easy to focus on one goal if you're just trying to maximize revenue, or if you're just trying to maximize, graduation rate. There's a lot of things you can do. It becomes more difficult when you have to focus on many things simultaneously, especially because some of these goals may conflict. The things that you do to maximize one may impair the other. And so when that happens, you actually need to start engaging in a deliberate process of optimization. You need to optimize. And there are ways that you can do this. If you have enough data, you can do a mathematical optimization to find the ideal balance of efforts to pursue one goal and the other goal at the same time. Now, this is a very general summary, and let me finish with this. In sum, metrics or methods for measuring can help awareness of how well your organization is functioning and how well you're reaching your goals. There are many different methods available for defining success and measuring progress towards those things. The trick, however, comes when you have to balance efforts to reach multiple goals simultaneously, which can bring in the need for things like optimization. When talking about data sourcing and measurement, one very important issue has to do with the accuracy of your measurements. The idea here is that you don't want to have to throw away all your ideas. You don't want to waste effort. One way of doing this in a very quantitative fashion is to make a classification table. So what that looks like is this. You talk about, for instance, positive results, negative results. And in fact, let's start by looking at the top here. The middle two columns here talk about whether an event is present, whether your house is on fire, whether a sale occurs, whether you've got a tax evader, whatever. So that's whether a particular thing is actually happening or not. On the left here is whether the test or the indicator suggests that a thing is or is not happening. And then you have these combinations of true positives, where the test says it's happening and it really is, and false positive, where the test says it's happening but it's not. And then below that, true negatives, where the test says it isn't happening and that's correct. And then false negatives, where the test says there's nothing going on, but there is in fact the event occurring. And then you start to get the column totals, the total number of events present or absent, and the row totals that talk about the test results. Now, from this table, what you get is 4 kinds of accuracy, or really 4 different ways of quantifying accuracy using different standards. And they go by these names: sensitivity, specificity, positive predictive value, and negative predictive value. I'll show you very briefly how each of them works. Sensitivity can be expressed this way. If there's a fire, does the alarm ring? You want that to happen. And so that's a matter of looking at the true positives and dividing that by the total number of alarms. So the test positive means there's an alarm, and the event present means there's a fire. You want always to have an alarm when there's a fire. Specificity, on the other hand, is sort of the flip side of this. If there isn't a fire, does the alarm stay quiet? This is where you're looking at the ratio of true negatives to total absent events, where there's no fire and the alarm's not ringing, and that's what you want. Now, those are looking at columns. You can also go sideways across rows. So the first one there is positive predictive value, often just abbreviated as PPV. And we flip around the order a little bit. This one says, if the alarm rings, was there a fire? So now you're looking at the true positives and dividing it by the total number of positives. Total number of positives is any time the alarm rings. True positives is because there was a fire. And negative predictive value, or NPV, says, if the alarm doesn't ring, does that in fact mean that there is no fire? Well, here you're looking at true negatives and dividing it by total negatives the time that it doesn't ring. And again, you want to maximize that so the true negatives account for all of the negatives, the same way you want the true positives to account for all of the positives, and so on. Now, you can put numbers on all of these going from 0% to 100%, and the idea is to maximize each one as much as you can. So in sum, from these tables, we get 4 kinds of accuracy, and there's a different focus for each one, but the same overall goal. You want to identify the true positives and true negatives and avoid the false positives and false negatives. And this is one way of putting numbers on, an index really, on the accuracy of your measurement. Now, data sourcing may seem like a very quantitative topic, especially when we're talking about measurement, but I want to measure one important thing here, and that is the social context of measurement. The idea here really is that people are people, and they all have their own goals and they're going their own ways, and we all have our own thoughts and feelings that don't always coincide with each other, and this can affect measurement. And so, for instance, when you're trying to define your goals and you're trying to maximize them, you want to look at things like, for instance, the business model. An organization's business model, the way they conduct their business, the way they make their money, is tied to its identity and its reason to be. And if you make a recommendation that's contrary to their business model, that can actually be perceived as a threat to their core identity, and people tend to get freaked out in that situation. Also, restrictions. So for instance, there may be laws, policies, and common practices, both organizationally and culturally, that may limit the ways that goals can be met. Now, most of these make a lot of sense. So the idea is you can't just do anything you want. You need to have these constraints. And when you make your recommendations, maybe you'll work creatively in them as long as you're still behaving legally and ethically. But you do need to be aware of these constraints. Next is the environment. And the idea here is that competition occurs both between organizations. That company here is trying to reach a goal, but they're competing with company B over there. But probably even more significantly, there is competition within the organization. This is really a recognition of office politics, and that when you as a consultant make a recommendation based on your analysis, you need to understand you're kind of dropping a little football into the office, and things are going to further one person's career, maybe to the detriment of another. And in order for your recommendations to have the maximum effectiveness, they need to play out well in the office. That's something that you need to be aware of as you're making your recommendations. Finally, there's the issue of manipulation. And a sad truism about people is that any reward system at all, will be exploited, and people will generally game the system. This happens especially when you have a strong cutoff. You need to get at least 80% or you get fired. And people will do anything to make their numbers appear to be 80%. This happens an awful lot when you look at executive compensation systems. It looks a lot when you have very high stakes school testing. It happens in an enormous number of situations. And so you need to be aware of the risk of exploitation and gaming. Now, don't think then that all is lost. Don't give up. You can still do really wonderful assessment. You can get good metrics. Just be aware of these particular issues and be sensitive to them as you both conduct your research and as you make your recommendations. So, in sum, social factors affect goals, and they affect the way that you meet those goals. There are limits and consequences both on how you reach the goals and how really what the goal should be, and that when you're making advice on how to reach those goals, please be sensitive to how things play out with metrics and how people will adapt their behavior to meet the goals. That way, you can make something that's more likely to be implemented the way you meant and more likely to predict accurately what can happen with your goals. When it comes to data sourcing, obviously the most important thing is to get data, but the easiest way to do that, at least in theory, is to use existing data. Think of it as going to the bookshelf and getting the data that you have right there at hand. Now, there's a few different ways to do this. You can get in-house data, you can get open data, and you can get third-party data. Another nice way to think of that is proprietary public, and purchased data, the 3 Ps I've heard it called. Let's talk about each of these a little bit more. So in-house data, that's stuff that's already in your organization. What's nice about that is it can be really fast and easy. It's right there. And the format may be appropriate for the kind of software and the computer that you're using. If you're fortunate, there's good documentation, although sometimes when it's in-house, people just kind of throw it together. So you have to watch out for that. And there's the issue of quality control. Now, this is true with any kind of data, but you need to pay attention with in-house because you don't know the circumstances necessarily under which people gathered the data and how much attention they were paying to something. There's also an issue of restrictions. There may be some data that while it's in-house, you may not be allowed to use, or you may not be able to publish the results or share the results with other people. So these are things that you need to think about when you're going to use in-house data in terms of how can you use it to facilitate your data science projects. Specifically, there are a few pros and cons. In-house data, potentially quick, easy, free. Hopefully it's standardized. Maybe even the original team that conducted this study is still there. And you might have identifiers in the data which make it easier for you to do an individual level analysis. On the con side, however, the in-house data simply may not exist. Maybe it's just not there. Or the documentation may be inadequate. And of course, the quality may be uncertain. It's always true, but maybe something you have to pay more attention to when you're using in-house data. Now, another choice is open data, like going to the library and getting something. This is prepared data that's freely available. It consists of things like government data and corporate data and scientific data from a number of sources. Let me show you some of my favorite open data sources, just so you know where they are and that they exist. Probably the best one is data.gov here in the US. That is it says right here, the home of the US government's open data. Or you may have a state level one. For instance, I'm in Utah and we have data.utah.gov, also a great source of more regional information. If you're in Europe, you have open-data.europa.eu, the European Union Open Data Portal. And then there are major nonprofit organizations. So the UN has unicef.org/statistics for their statistical and monitoring data. The World Health Organization has the Global Health Observatory at who.int/GHO. And then there are private organizations that work in the public interest, such as the Pew Research Center, which shares a lot of its data sets, and the New York Times, which makes it possible to use APIs to access a huge amount of the data of things they've published over a huge time span. And then two of the mother loads, there's Google, which at google.com has public data, which is a wonderful thing. And then Amazon at aws.amazon.com datasets has gargantuan datasets. So if you needed a dataset that was like 5 terabytes in size, this is the place that you would go to get it. Now, there's some pros and cons to using this kind of open data. First is that you can get very valuable datasets that maybe cost millions of dollars to gather and to process. And you can get a very wide range of topics and times and groups of people and so on. And often the data is very well formatted and well documented. There are, however, a few cons. Sometimes there's biased samples. Say, for instance, you only get people who have internet access, and that can mean, not everybody. Sometimes the meaning of the data is not clear, or it may not mean exactly what you want it to. A potential problem is that sometimes you may need to share your analyses. And if you're doing proprietary research, well, it's going to have to be open research instead. And so that can create a crimp with some of your clients. And then finally, there are issues with privacy and confidentiality. And in public data, that usually means that the identifiers are not there, and you're going to have to work at a larger aggregate level of measurement. Another option is to use data from a third party. These go by the name Data as a Service, or DAS. You can also call them data brokers. And the thing about data brokers is they can give you an enormous amount of data on many different topics. Plus, they can save you some time and effort by actually doing some of the processing for you. And that can include things like consumer behaviors and preferences. They can get contact information. They can do marketing, identity, and finances. There's a lot of things. There's a number of data brokers around. Here's a few of them. Axiom is probably the biggest one in terms of marketing data. There's also Nielsen, which provides data primarily for media consumption. And there's another organization, DataSift. That's a smaller, newer one. And there's a pretty wide range of choices, but these are some of the big ones. Now, the thing about using data brokers, there's some pros and there's some cons. The pros are first that it can save you a lot of time and effort. It can also give you individual level data, which can be hard to get from open data. Open data is usually at the community level. They can give you information about specific consumers. They can even give you summaries and inferences about things like credit scores and marital status, possibly even whether a person gambles or smokes. Now, the con is this. Number one, it can be really expensive. This is a huge service. It provides a lot of benefit and is priced accordingly. Also, you still need to validate it. You still need to double check that it means what you think it means and that it works in with what you want. And probably a real sticking point here is the use of third-party data is distasteful to many people. And so you have to be aware of that as you're making your choices. So in sum, as far as data sourcing existing data goes, obviously, data science needs data, and there's the 3 Ps of data sources: proprietary and public and purchased. But no matter what source you use, you need to pay attention to quality and to the meaning and the usability of the data to help you along in your own projects. When it comes to data sourcing, a really good way of getting data is to use what are called APIs. Now, I like to think of these as the digital version of Prufrock's Mermaids, if you're familiar with the love song of J. Alfred Prufrock by T.S. Eliot. He says, "I have heard the mermaids singing each to each." That's T.S. Eliot. And I like to adapt that to say, APIs have heard apps singing each to each. And that's by me. Now, more specifically, when we talk about an API, what we're talking about is something called an application programming interface. And this is something that allows programs to talk to each other. Its most important use in terms of data science is it allows you to get web data. It allows your program to directly go to the web on its own, grab the data, bring it back in, almost as though it were local data. And that's a really wonderful thing. Now, the most common version of APIs for data science are called REST APIs. That stands for Representational State Transfer. That's the software architectural style of the World Wide Web. And it allows you to access data on web pages via HTTP. That's the Hypertext Transfer Protocol that, runs the web as we know it. And when you download the data, you usually get it in JSON format. That stands for JavaScript Object Notation. The nice thing about that is that's human readable, but it's even better for machines. Then you can take that information and you can send it directly to other programs. And the nice thing about REST APIs is that they're what's called language agnostic, meaning any programming language can call a REST API, can get data from the web, and can do whatever it needs to with it. Now, there are a few kinds of APIs that are really common. The first is what are called social APIs. These are ways of interfacing with social networks. So for instance, the most common is Facebook. There's also Twitter. Google Talk has been a big one, and Foursquare as well. And then SoundCloud. These are on lists of the most popular ones. And then there are also what are called visual APIs, which are for getting visual data. So for instance, Google Maps is the most common. But YouTube, something that accesses YouTube on a particular website, or AccuWeather, which is for getting weather information, Pinterest for photos, and Flickr for photos as well. So these are some really common APIs, and you can program your computer to pull in data from any of these services and sites and integrate it into your own website or here into your own data analysis. Now, there's a few different ways you can do this. You can program it in R, the statistical programming language. You can do it in Python. Also, you can even do it in the very basic Bash command line interface. And there's a ton of other applications. Basically, anything can access an API one way or another. Now, I'd like to show you how this works in R. So I'm going to open up a script in RStudio, and then I'm going to use it to get some very basic information from a web page. Let me go to RStudio and show you how this works. I've opened up a script in RStudio that allows me to do some data sourcing here. Now, I'm just going to use a package called JSON Lite. I'm going to load that one up. And then I'm going to go to a couple of websites. I'm going to be getting historical data from Formula One car races, and I'm going to be getting it from airgas.com. Now, if we go to this page right here, I can just go straight to my browser right now. And this is what it looks like. It gives you the API documentation. So what you're doing for an API is you're just entering a web address, and in that web address, it includes the information that you want. I'll go back to R here for a second. And if I want to get information about 1957 races in JSON format, I go to this address, and I can skip over to that for a second. And what you see is it's kind of a big long mess here, but it is all labeled and it's clear to the computer what's going on here. I'll go back to R. And so what I'm going to do is I'm going to save that URL into an object here in R. And then I'm going to use the command from JSON to read that URL and save it into R, and which it is now done. And I'm going to zoom in on that so you can see what's happened. I've got this sort of mess of text. This is actually a list object in R. And then I'm going to get just the structure of that object. So I'm going to do this one right here. And you can see that it's a list, and it gives you the names of all the variables within each one of the lists. And what I'm going to do is I'm going to convert that list to a data frame I went through the list and found exactly where the information I wanted was located. You have to use this big, long statement here. That'll give me the names of the drivers. Let me zoom in on that again. There they are. And then I'm going to get just the column names for that bit of the data frame. And so what I have here is 6 different variables. And then what I'm going to do is I'm going to pick just the first 5 cases, and I'm going to select some variables and put them in a different order. And when I do that, this is what I get. I'll zoom in on that again. And the first 5 people listed in this data set that I pulled in from 1957 are Juan Fangio, makes sense, one of the greatest drivers ever, and other people who competed in that year. And so what I've done is by using this API call in R, it's a very simple thing to do, I was able to pull data off that web page in a structured format and do a very simple analysis with it. And let's sum up what we've learned from all of this. First off, APIs make it really easy to work with web data. They structure it, they call it for you, and then they feed it straight into the programs for you to analyze. And they're one of the best ways of getting data and getting started in data science. When you're looking for data, another great way of getting data is through scraping. And what that means is pulling information from web pages. I like to think of it as when data is hiding in the open. It's there, you can see it, but there's not an easy, immediate way to get that data. Now, when you're dealing with scraping, you can get data in several different formats. You can get HTML text from web pages. You can get HTML tables, the rows and columns that appear on web pages. You can scrape data from PDFs, and you can scrape data from all sorts of media like images and video and audio. Now, we'll make one very important qualification before we say anything else. Pay attention to copyright and privacy. Just because something is on the web doesn't mean you're allowed to pull it out. Information gets copyrighted. And so when I use examples here, I make sure that this is stuff that's publicly available, and you should do the same when you're doing your own analyses. Now, if you want to scrape data, there's a couple of ways to do it. Number one is to use apps that are developed for this. So for instance, import.io is one of my favorites. It's both a web page, that's its address, and it's a downloadable app. There's also ScraperWiki. There's an application called Tabula, and you can even do scraping in Google Sheets, which I'll demonstrate in a second, and Excel. Or if you don't want to use an app, or if you want to do something that apps don't really let you do, you can code your scraper. You can do it directly in R, or Python, or Bash, or even Java or PHP. Now, what you're going to do is you're going to be looking for information on the web page. If you're looking for HTML text, what you're going to do is you're going to pull structured text from web pages, similar to how a reader view works in a browser. it uses HTML tags on the web page to identify what's the important information. So that's things like body and H1 for header 1 and P for paragraph in the angle brackets. You can also get information from HTML tables, although this is a physical table of rows and columns I'm showing you. This also uses HTML table tags. That's like table and TR for table row and TD for table data. That's a cell. The trick is when you're doing this, you need the table number, and sometimes you just have to find that through trial and error. Let me give you an example of how this works. Let's take a look at this Wikipedia page on the Iron Chef America competition. I'm going to go to the web right now and show you that one. So here we are in Wikipedia, Iron Chef America. And if you scroll down a little bit, you see we got a whole bunch of text here, and we got our table of contents. And then we come down here, we have a table that lists the winners, the statistics for the winners. And let's say we want to pull that from this web page into another program for us to analyze. Well, there's an extremely easy way to do this with Google Sheets. All we need to do is open up a Google Sheet, and in cell A1 of that Google Sheet, we paste in this formula. It's import HTML, then you give the web page, then you say that you're importing a table. You have to put that stuff in quotes, and the index number for the table. I had to poke around a little bit to figure out that this one was table number 2. So let me go to Google Sheets and show you how this works. Here I have a Google Sheet, and right now it's got nothing in it, but watch this. If I come here to this cell and I simply paste in that information, all this stuff just sort of magically propagates into the sheet, makes it extremely easy to deal with. And now I can, for instance, save this as a CSV file, put it in another program, lots of options. And so this is one way that I'm scraping the data from a web page because I didn't use an API, but I just use a very simple one-line command in Google Sheets to get the information. Now that was an HTML table. You can also scrape data from PDFs. You have to be aware of whether it's a native PDF, I call that a text PDF, or a scanned or image PDF. And what it does with native PDFs is it looks for text elements. Again, those are like code that indicates this is text. And you can deal with raster images, that's pixel images, or vector, which draws the lines, and that's what makes them infinitely scalable in many situations. And then in PDFs, you can deal with tabular data, but you probably have to use a specialized program like Scraper, Wiki, or Tabula in order to get that. And then finally, media like images and video and audio. Getting images is easy. You can download them in a lot of different ways. And then if you want to read data from them, say for instance, you have a heat map of a country, you can go through it, but you'll probably have to write a program that loops through the image pixel by pixel to read the data and then encode it numerically into your statistical program. Now that's my very brief summary, and let's summarize that. First off, if the data you're trying to get at doesn't have an existing API, you can try scraping. And you can use specialized apps for scraping, or you can write code in a language like R or Python. But no matter what you do, be sensitive to issues of copyright and privacy so you don't get yourself in hot water, but instead you make an analysis that can be of great use to you or to your client. The next step in data sourcing is making data, and specifically we're talking about getting new data. I like to think of this as you're getting your hands on and you're getting data de novo, new data. So, can't find the data that you need for your analysis? Well, one simple solution is do it yourself. And we're going to talk about a few general strategies used for doing that. Now, these strategies vary on a few dimensions. First off is the role. Are you passive and simply observing stuff that's happening already? Or are you active where you play a role in creating the situation to get the data? And then there's the QQ question, and that is, are you going to get quantitative or numerical data? Or are you going to get qualitative data, which usually means text, paragraphs, sentences, as well as things like photos and videos and audio? And also, how are you going to get the data? Do you want to get it online or do you want to get it in person? Now, there's other choices than these, but these are some of the big delineators of the different methods. When you look at those, you get a few possible options. Number one is interviews, and I'll say more about those. Another one is surveys. A third one is card sorting. And a fourth one is experiments, although I actually want to split experiments into two kinds of categories. The first one is laboratory experiments, and that's in-person projects where you shape the information or an experience for the participants as a way of seeing how that involvement changes their reactions. Doesn't necessarily mean that you're a participant, but you create the situation. And then there's also A/B testing. This is automated online testing of 2 or more variations on a web page. It's a very, very simple kind of experimentation that's actually very useful for optimizing websites. So, in sum, from this very short introduction, make sure you can get exactly what you need. Get the data you need to answer your question. And if you can't find it somewhere, then make it. And as always, you have many possible methods, each of which have their own strengths and their own compromises. And we'll talk about each of those in the following sections. The first method of data sourcing where you're making new data that I want to talk about is interviews. And that's not because it's the most common, but because it's the one you would do for the most basic problem. Now, basically, an interview is nothing more than a conversation with another person or a group of people. And the fundamental question is, why do interviews as opposed to doing a survey or something else? Well, there's a few good reasons to do that. Number one, you're working with a new topic and you don't know what people's responses will be or how they'll react. And so you need something very open-ended. Number two, you're working with a new audience. You don't know how they will react in particular to what it is you're trying to do. And number three, something's going on with the current situation. It's not working anymore, and you need to find what's going on, and you need to find ways to improve. The open-ended information where you get past your existing categories and boundaries can be one of the most useful methods for getting that data. If you want to put it another way, you want to do interviews when you don't want to constrain responses. Now, when it comes to interviews, you have one very basic choice, and that's whether you do a structured interview. And with a structured interview, you have a predetermined set of questions, and everyone gets the same questions in the same order. It gives a lot of consistency, even though the responses are open-ended. And then you can also have what's called an unstructured interview. And this is a whole lot more like a conversation where you as the interviewer and the person you're talking to, your questions arise in response to their answers. Consequently, an unstructured interview can be different for each person that you talk to. Also, interviews are usually done in person, but not surprisingly, they can be done over the phone or often online. Now, a couple of things to keep in mind about interviews. Number one is time. Interviews can range from just a few minutes to several hours per person. Second is training. Interviewing is a special skill that usually requires specific training. Now, asking the questions is not necessarily the hard part. The really tricky part is the analysis. The hardest part of interviews by far is analyzing the answers for themes and way of extracting the new categories and the dimensions that you need for your further research. The beautiful thing about interviews is they allow you to learn things that you never expected. So, in sum, interviews are best for new situations or new audiences. On the other hand, they can be time-consuming, and they also require special training, both to conduct the interview, but even more to analyze the highly qualitative data that you get from them. An interesting topic in data sourcing when you're making data is card sorting. Now, this isn't something that comes up very often in academic research, but in web research, this can be a really important method. Think of it as what you're trying to do is like building a model of a molecule here. You're trying to build a mental model or a model of people's mental structures. Put more specifically, how do people organize information intuitively? And also, how does that relate to the things that you're doing online? Now, the basic procedure goes like this. You take a bunch of little topics and you write each one on a separate card. And you can do this physically with like 3x5 cards, or there's a lot of programs that allow you to do a digital version of it. Then what you do is you give this information to a group of respondents and the people sort those cards. So they put similar topics with each other, different topics over here, and so on. And then you take that information, and from that, you're able to calculate what's called dissimilarity data. Think of it as like the distance or the difference between various topics. And that gives you the raw data to analyze how things are structured. Now, there are two very general kinds of card sorting tasks. There are generative and there's evaluative. A generative card sorting task is one in which respondents create their own sets, their own piles of cards using any number of groupings they like. And this might be used, for instance, to design a website. If people are going to be looking for one kind of information next to another one, then you want to put that together on the website so they know where to expect it. On the other hand, if you've already created a website, then you can do an evaluative card sorting. This is where you have a fixed number or fixed names of categories, like for instance, the way you've set up your menus already. And then what you do is you see if people naturally put the cards into these various categories that you've created. That's a way of verifying that your hierarchical structure makes sense to people. Now, whichever method you do, generative or evaluative, what you end up with when you do a card structure is an interesting kind of visualization. It's called a dendrogram. That actually means branches. And what we have here is actually 150 data points. If you're familiar with Fisher's iris data, that's what's going on here. And it groups it from one giant group on the left and then splits it in pieces and pieces and pieces until you end up with lots of different individual level observations at the end. But you can cut things off into 2 or 3 groups or wherever it's most useful for you here as a way of visualizing the entire collection of similarity or dissimilarity between the individual pieces of information that you had people sort. Now, I'll just mention very quickly, if you want to do digital card sorting, which makes your life infinitely easier because keeping track of physical cards is really hard, you can use something like Optimal Workshop or User Zoom or UX Suite. These are some of the most common choices. Now, let's just sum up what we've learned about card sorting in this extremely brief overview. Number 1, card sorting allows you to see intuitive organization of information in a hierarchical format. You can do it with physical cards, or you also have digital choices for doing the same thing. And when you're done, you actually get this hierarchical or branched visualization of how the information is structured and related to each other. When you're doing your data sourcing and you're making data, sometimes you can't get what you want through the easy ways, and you got to take the hard way. And you can do what I'm calling laboratory experiments. Now, of course, when I mention laboratory experiments, people start to think of stuff like, Dr. Frankenstein in his lab, but lab experiments are less like this. And in fact, they're a little more like this. Nearly every experiment I have done in my career has been a paper and pencil one with people in a well-lighted room, and it's not been the threatening kind. Now, the reason you do a lab experiment is because you want to determine cause and effect. And this is the single most theoretically viable way of getting that information. Now, what makes an experiment is the fact that researchers play active roles in experiments with manipulations. Now, people get a little freaked out when they hear manipulations, think that you're coercing people and messing with their mind. All that means is you are manipulating the situation. You're causing something to be different for one group of people or one situation than another. It's a benign thing, but it allows you to see how people react to those different variations. Now, you're going to want to do an experiment. You're going to want to have focused research. It's usually done to test one thing or one variation at a time. And it's usually hypothesis driven. Usually you don't do an experiment until you've done enough background research to say, I expect people to react this way to this situation and this way to the other. A key component of all of this is that experiments almost always have random assignments. So regardless of how you got your sample, when they're in your study, you randomly assign them to one condition or another. And what that does is it balances out the pre-existing differences between groups. And that's a great way of taking care of confounds and artifacts, the things that are unintentionally associated with differences between groups that provide alternate explanations for your data. If you've done good random assignment and you have a large enough people, then those confounds and artifacts are basically minimized. Now, some places where you're likely to see laboratory experiments in this version are, for instance, eye tracking and web design. That's where you have to bring people in front of a computer and you stick a thing there that sees where they're looking. That's how we know, for instance, that people don't really look at ads on the side of web pages. Another very common place is research in medicine and education, and in my field, psychology. And in all of these, what you find is that experimental research is considered the gold standard for reliable, valid information about cause and effect. On the other hand, while it's a wonderful thing to have, it does come at a cost. Here's how that works. Number one, experimentation requires extensive specialized training. It's not a simple thing to pick up. Two, experiments are often very time-consuming and labor-intensive. I've known some that take hours per person. And number three, experiments can be very expensive. So what that all means is you want to make sure that you've done enough background research, and you need to have a situation where it's sufficiently important to get really reliable cause and effect information to justify these costs for experimentation. In sum, laboratory experimentation is generally considered the best method for causality or assessing causality. That's because it allows you to control for confounds through randomization. On the other hand, it can be difficult to do, so be careful and thoughtful when considering whether you need to do an experiment and how to actually go about doing it. There's one final procedure I want to talk about in terms of data sourcing and making new data. It's a form of experimentation, and it's simply called A/B testing, and it's extremely common in the web world. So for instance, I just barely grabbed a screenshot of Amazon.com's homepage, and you've got these various elements on the homepage. And I just noticed, by the way, when I did this, that this woman is actually a animated GIF. So she moves around. That was kind of weird. Never seen that before. But the thing about this is this entire layout, how things are organized and how they're on there, will have been determined by variations on A/B testing by Amazon. Here's how it works. For your web page, you pick one element, like what's the headline, or what are the colors, or what's the organization, or how do you word something, and you create multiple versions, maybe just two, version A and version B, which is why you called A/B testing. And then when people visit your web page, you randomly assign those visitors to one version or another. You have software that does that for you automatically. And then you compare the response rates on some response. I'll show you those in a second. And then once you have enough data, you implement the best version, you sort of set that one solid, and then you go on to something else. Now, in terms of response rates, there's a lot of different outcomes you can look at. You can look at how long a person's on a page. You can actually do mouse tracking if you want to. You can look at click-throughs. You can also look at shopping cart value or abandonment. A lot of possible outcomes. All of these contribute through A/B testing to the general concept of website optimization, to make your website as effective as it can possibly be. Now, the idea also is that this is something you're going to do a lot. You can perform A/B tests continually. In fact, I've seen one person say that what A/B testing really stands for is always be testing. Kind of cute, but it does give you the idea that improvement is a constant process. Now, if you want some software to do A/B testing, two of the most common choices are Optimizely and VWO, which stands for Visual Web Optimizer. Now, many others are available, but these are especially common. And when you get the data, you're going to use statistical hypothesis testing to compare the differences, or really, the software does it for you automatically, but you may want to adjust the parameters because most software packages cut off testing a little too soon and the information is not quite as reliable as it should be. But in sum, here's what we can say about A/B testing. It's a version of website experimentation. It's done online, which makes it really easy to get a lot of data very quickly. It allows you to optimize the design of your website for whatever outcome is important to you. And it can be done as a series of continual assessments, testing, and development to make sure that you're accomplishing what you want to as effectively as possible for as many people as possible. The next logical step in data sourcing and making data is surveys. Now, think of this. If you want to know something, just ask. That's the easy way. And you want to do a survey under certain situations. The real question is, do you know your topic and your audience well enough to anticipate their answers, to know what the range of their answers and the dimensions and the categories that are going to be important? If you do, then a survey might be a good approach. Now, just as there were a few dimensions for interviews, there's a few dimensions for surveys. You can do what's called a closed-ended survey. That's also called a forced choice. It's where you give people just particular options, like a multiple choice. You can have an open-ended survey where you have the same questions for everybody, but you allow them to write in a free-form response. You can do surveys in person, and you can also do them online or over the mail or phone or however. And now it's very common to use software when doing surveys. Some really common applications for online surveys are SurveyMonkey and Qualtrics, or at the very simple end, there's Google Forms, and at the simple and pretty end, there's Typeform. There's a lot more choices, but these are some of the major players in how you can get data from online participants in survey format. Now, the nice thing about surveys is, they're really easy to do. They're very easy to set up, and they're really easy to send out to large groups of people. You can get tons of data really fast. On the other hand, the same way that they're easy to do, they're also really easy to do badly. The problem is that the questions you ask, they can be ambiguous, they can be double-barreled, they can be loaded, and the response scales can be confusing. So if you say, I never think this particular way, and a person puts strongly disagree, they may not know exactly what you're trying to get at. So you have to take special effort to make sure that the meaning is clear, unambiguous, and that the rating scale, the way that people respond, is very clear and they know where their answer falls. Which gets us into one of the things about people behaving badly, and that is beware the push-pull. Now, especially during election time, like we're in right now, a push-pull is something that sounds like a survey, but really what it is a very biased attempt to get data, just fodder for social media campaigns, or I'm going to make a chart that says that 98% of people agree with me. A push-pull is one that's so biased, there's really only one way to answer to the questions. This is considered extremely irresponsible and unethical from a research point of view. Just hang up on them. Now, aside from that egregious violation of research ethics, you do need to do other things like watch out for bias in the question wording, in the response options, and also in the sample selection, because any one of those can push your responses off one way or another without you really being aware that it's happening. So in sum, let's say this about surveys. You can get lots of data quickly. On the other hand, it requires familiarity with the possible answers in your audience, so you know sort of what to expect. And no matter what you do, you need to watch for bias to make sure that your answers are going to be representative of the group that you're really concerned about understanding. The very last thing I want to talk about in terms of data sourcing is to talk about the next steps. And probably the most important thing is, don't just sit there. I want you to go and see what you already have. Try to explore some open data sources. And if it helps, check with a few data vendors. And if those don't give you what you need to do your project, then consider making new data. Again, the idea here is get what you need and get going. Thanks for joining me, and good luck on your own projects. Welcome to Coding in Data Science. I'm Barton Poulson, and what we're going to do in this series of videos is we're going to take a little look at the tools of data science. So I'm inviting you to know your tools, but probably even more important than that is to know their proper place. Now, I mention that because a lot of the times when people talk about data tools, they talk about it as though that were the same thing as data science, as though they were the same set. But I think if you look at it for just a second, that's not really the case. Data tools are simply one element of data science, because data science is made up of a lot more than the tools that you use. It includes things like business knowledge. It includes the meaning making and interpretation. It includes social factors. And so there's much more than just the tools involved. That being said, you will need at least a few tools. And so we're going to talk about some of the things that you can use in data science if it works well for you. In terms of getting started, the basic things, number one is spreadsheets. It's the universal data tool, and I'll talk about how they play an important role in data science. Number two is a visualization program called Tableau. There's Tableau Public, which is free, and there's Tableau Desktop, and there's also something called Tableau Server. But Tableau is a fabulous program for data visualization, and I'm convinced for most people provides the great majority of what they need. And though, while it's not a tool, I do need to talk about the formats used in web data because you have to be able to navigate that when doing a lot of data science work. Then we can talk about some of the essential tools for data science. Those include the programming language R, which is specifically for data, There's the general purpose programming language Python, which has been well adapted to data. And there's the database language SQL, or SQL for structured query language. Then if you want to go beyond that, there are some other things that you can do. There are the general purpose programming languages C, C++, and Java, which are very frequently used to form the foundation of data science, and sort of high-level production code is going to rely on those as well. There's the command line interface language Bash, which is very common as a very quick tool for manipulating data. And then there's the sort of wildcard, supercharged regular expressions, or regex. We'll talk about all of these in separate courses. But as you consider all the tools that you can use, don't forget the 80-20 rule, also known as the Pareto principle. And the idea here is that you're going to get a lot of bang for your buck out of a small number of things. And I'm going to show you a little sample graph here. Imagine that you have 10 different tools, and we'll call them A through B. A does a lot for you, B does a little bit less, and it kind of tapers down to you've got a bunch of tools that do just a little bit of stuff that you need. Now, instead of looking at the individual effectiveness, look at the cumulative effectiveness. How much are you able to accomplish with a combination of tools? Well, the first one's right here at 60% where the tool started. Then you add on the 20% from B and it goes up, and then you add on C and D, and you add up little smaller pieces. And by the time you get to the end, you've got 100% of effectiveness from your 10 tools combined. The important thing about this is you only have to go to the second tool. That's 2 out of 10. So that's B, that's 20% of your tools. And in this made up example, you've got 80% of your output. So 80% of the output from 20% of the tools. That's a fictional example of the Pareto principle, but I find in real life it tends to work something approximately like that. And so you don't necessarily have to learn everything, and you don't have to learn how to do everything in everything. Instead, you want to focus on the tools that will be most productive, and specifically most productive for you. So in sum, let's say these 3 things. Number 1, coding, or simply the ability to manipulate data with programs and computers. Coding is important, but data science is much greater than the collection of tools that's used in it. And then finally, as you're trying to decide what tools to use and what you need to learn and how to work, remember the 80-20 rule. You're going to get a lot of bang from a small set of tools. So focus on the things that are going to be most useful for you in conducting your own data science projects. As we begin our discussion of coding and data science, I actually want to begin with something that's not coding. I want to talk about applications, or programs that are already created that allow you to manipulate data. And we're going to begin with the most basic of these, spreadsheets. We're going to do the rows and columns and cells of Excel. And the reason for this is you need spreadsheets. Now, you may be saying to yourself, no, not me. Because you know what? I'm fancy. I'm working in my big set of servers. I got fancy things going on. But you know what? You two fancy people, you need spreadsheets as well. And there's a few reasons for this. Most importantly, spreadsheets can be the right tool for data science in a lot of circumstances. There are a few reasons for that. Number 1, spreadsheets, they're everywhere. They're ubiquitous. They're installed on 1 billion machines around the world. And everybody uses them. They probably have more data sets in spreadsheets than anything else. And so it's a very common format. Importantly, it's probably your client's format. A lot of your clients are going to be using spreadsheets for their own data. I've worked with billion-dollar companies that keep all of their data in spreadsheets. And so when you're working with them, you need to know how to manipulate that and how to work with it. Also, regardless of what you're doing, spreadsheets, or specifically CSV, comma-separated value files, are sort of the lingua franca, the universal interchange format for data transfer to allow you to take it from one program to another. And then, truthfully, in a lot of situations, they're really easy to use. And if you want a second opinion on this, let's take a look at this ranking that is a survey of data mining experts. It's the KD Nuggets data mining poll. And these are the tools they most use in their own work. And look at this. Lowly Excel is 5th on the list. And in fact, what's interesting about it, It's above Hadoop and Spark, two of the major big data fancy tools. And so Excel really does have a place of pride in a toolkit for a data analyst. Now, since we're going to sort of the low-tech end of things, let's talk about some of the things that you can do with a spreadsheet. Number one, they're really good for data browsing. You actually get to see all of the data in front of you, which isn't true if you're doing something like R or Python. They're really good for sorting data. Sort by this column, then this column, then this column. They're really good for rearranging columns and cells and moving things around. They're good for finding and replacing and seeing what happened so you know that it worked right. Some more uses. They're really good for formatting, especially conditional formatting. They're good for transposing data, switching the rows and the columns. They make that really easy. They're good for tracking changes. Now, it's true if you're a big fancy data scientist, you're probably using GitHub. But for everybody else in the world, spreadsheets and the tracking changes is a wonderful way to do it. You can make pivot tables. That allows you to explore the data in a very hands-on way, in a very intuitive way. And they're also really good for arranging the output for consumption. Now, when you're working with spreadsheets, however, there's one thing you need to be aware of. They're really flexible, but that flexibility can be a problem, and that when you're working in data science, you specifically want to be concerned about something called tidy data. That's a term I borrowed from Hadley Wickham, very well-known developer in the R world. Tidy data is for transferring data and making it work well. There's a few rules here that undo some of the flexibility inherent in spreadsheets. Number one, what you want to do is have a column be equivalent to the same thing as a variable. Columns, variables, they are the same thing. And then rows are exactly the same thing as cases. And then you have one sheet per file, and then you have one level of measurement, say individual, then organization, then state per file. Again, this is undoing some of the flexibility that's inherent in spreadsheets, but it makes it really easy to move the data from one program to another. Let me show you how all this works. You can try this in Excel. If you've downloaded the files for this course, we simply want to open up this spreadsheet. Let me go to Excel and show you how it works. So when you open up the spreadsheet, what you get is totally fictional data here that I made up, but it's showing sales over time of several products at two locations, like if you're selling stuff at a baseball field. And this is the way spreadsheets often appear. We got blank rows and columns. We got stuff arranged in a way that makes it easy for the person to process it. And we got totals here and with formulas, putting them all together. And that's fine. That works well for the person who made it. And then that's for 1 month. And then we have another month right here. And then we have another month right here. And then we combine them all for the first quarter of 2014. We've got some headers here. And we've got some conditional formatting and changes. And if we come to the bottom, we've got a very busy line graphic that eventually loads. It's not a good graphic, by the way, but similar to what you will often find. So this is the stuff that, while it may be useful for the client's own personal use, you can't feed this into R or Python. It'll just choke and it won't know what to do with it. And so you need to go through a process of tidying up the data. And what this involves is undoing some of this stuff. So for instance, here's data that is almost tidy. Here we have a single column for the date, a single column for the day, a column for the site. So we have two locations, A and B. And then we have 6 columns for the 6 different things that are sold and how many were sold on each day. Now, in certain situations, you would want the data laid out exactly like this. If you're doing, for instance, a time series, you'll do something vaguely similar to this. But for true tidy stuff, we're going to collapse it even further. Let me come here to the tidy data. And now what I've done is I've created a new column that says, what is the item being sold? And so, by the way, what this means is that we've got a really long data set now. It's got over 1,000 rows. Come back up to the top here. But what that shows you is that now it's in a format that's really easy to import from one program to another. That makes it tidy, and you can remanipulate it however you want once you get to each of those. So let's sum up our little presentation here in a few lines. Number one, no matter who you are, no matter what you're doing in data science, you need spreadsheets. And the reason for that is that spreadsheets are often the right tool for data science. Keep one thing in mind though, and that is as you're moving back and forth from one language to another, tidy data or well-formatted data is going to be important for exporting data into your analytical programmer language of choice. As we move through coding and data science, and specifically the applications that can be used, there's one that stands out for me more than almost anything else, and that's Tableau and Tableau Public. Now, if you're not familiar with these are visualization programs. The idea here is that when you have data, the most important thing you can do is to first look and see what you have and work with it from there. And in fact, I'm convinced that for many organizations, Tableau might be all that they really need. It will give them the level of insight that they need to work constructively with data. So let's take a quick look by going to tableau.com. Now there are a few different versions of Tableau. Right here we have Tableau Desktop and Tableau Server, and these are the paid versions of Tableau. They actually cost a lot of money unless you work for a nonprofit organization, in which case you can get them for free, which is a beautiful thing. What we're usually looking for, however, is not this paid version, but we're looking for something called Tableau Public. And if you come in here and go to products, and we've got these three paid ones, come over here to Tableau Public. And we click on that, it brings us to this page. It's public.tableau.com. And this is the one that has what we want. It's a free version of Tableau with one major caveat. You don't save files locally to your computer, which is why I didn't give you a file to open. Instead, it saves them to the web in a public form. So if you're willing to trade privacy, you can get an immensely powerful application for data visualization. That's a catch for a lot of people, which is why people are willing to pay a lot of money for the desktop version. And again, if you work for a nonprofit, you can get the desktop version for free. But I'm going to show you how things work in Tableau Public. So that's something that you can work with personally. The first thing you want to do is you want to download it. And so you put in your email address, you download, it's going to know what you're on. It's a pretty big download. And once it's downloaded, you can install it and open up the application. And here I am in Tableau Public right here. This is the blank version. By the way, you also need to create an account with Tableau in order to save your stuff online and to see it. We'll show you what that looks like. But you're presented with a blank thing right here. And the first thing you need to do is you need to bring in some data. I'm going to bring in an Excel file. Now, if you've downloaded the files for the course, you'll see that there's this one right here, DSO322 Tableau Public .xlsx. It's a Excel file, and in fact, it's the one that I used in talking about spreadsheets in the first video in this course. I'm going to select that one, and I'm going to open it. And a lot of programs don't like bringing in Excel because it's got all the worksheets and all the weirdness in it. This one works better with it, but what I'm going to do is I'm going to take the tidy data. By the way, you see that it put them in alphabetical order here. And I'm going to take tiny data, and I'm just going to drag it over to let it know that it's the one that I want. And now what it does is it shows me a version of the data set along with things that you can do here. You can rename it. You can create bin groups. There's a lot of things that you can do here. I'm going to do something very, very quick with this particular one. Now I've got the data set right here. What I'm going to do now is I'm going to go to a worksheet. That's where you actually create stuff. Cancel that and go to worksheet 1. Okay, this is a drag and drop interface. And so what we're going to do is we're going to pull the bits and pieces of information we want to make graphics. There's immense flexibility here. I'm going to show you two very basic ones. I'm going to look at the sales of my fictional ballpark items. So I'm going to grab sales right here. And I'm going to put that as the field that we're going to measure. Okay, and you see it put it down right here. And this is our total sales. We're going to break it down by item and by time. So let me take item right here. And you can drag it over here, or I can put it right up here into rows. Those will be my rows, and that's how many we've sold total of each of the items. Fine, that's really easy. And then let's take date. and we'll put that here in columns to spread it across. Now, by default, it's doing it by year. I don't want to do that. I only have 3 months of data. And so what I can do is I can click right here and I can choose a different time frame. I can go to quarter, but that's not going to help because I only have 1 quarter's worth of data. That's 3 months. I'm going to come down to week. Actually, let me go to day. If I do day, you see it gets enormously complicated, so that's no good. So I'm going to back up to week. And I've got a lot of numbers there, but what I want is a graph. And so to get that, I'm going to come over here and click on this and tell it that I want a graph. And so we're seeing the information, except it lost item. So I'm going to bring item and I'm going to put it back up into this graph to say this is a row for the data. And now I've got rows for sales by week for each of my items. That's great. I want to break it down one more by putting in the site, the place that it's sold. And so I'm going to grab that and I'm going to put it right over here. And now you see I've got it broken down by the item that is sold and the different sites. And I'm going to color the sites. And all I got to do to that is I'm going to grab site and drag it onto color. Now I've got 2 different colors for my sites. And this makes it a lot easier to tell what's going on. And in fact, there's some other cool stuff you can do. One of the things I'm going to do is I can come over here to analytics and I can tell it, for instance, to put an average line through everything. So I'll just drag this over here and say, now we have the average for each line. That's good. And I can even do forecasting. Let me get a little bit of a forecast right here. I'll drag this on. And if you go over here, I can get this out of the way for a second. Now I have a forecast for the next few weeks. And that's a really convenient, quick and easy thing. And again, for some organizations, that might be all that they really need. And so what I'm showing you here is the absolute basic operation of Tableau, which allows you to do an incredible range of visualizations and manipulate the data and create interactive dashboards. There's so much to it, and we'll show that in another course. But for right now, I want to show you one last thing about Tableau Public, and that is saving the files. So now when I come here and save it, it's going to ask me to sign into Tableau Public. Now I sign in, and it asks me how I want to save this. Same name as the video. There we go, and I'm going to hit save. And then that opens up a web browser, and since I'm already logged into my account, see, here's my account, my profile. Here's the page that I created. And it's got everything I need there. I'm going to edit just a few details. I'm going to say, for instance, I'm going to leave its name like that. I could put more of a description in there if I wanted. I can allow people to download the workbook and its data. I'm going to leave that there so you can download it if you need to. If I had more than one tab, I would do this thing that says show the different sheets as tabs. Hit save. And there's my data set. And also, it's published online and people can now find it. And so what you have here is an incredible tool for creating interactive visualizations. You can create them with drop-down menus and you can rearrange things and you can make an entire dashboard. It's a fabulous way of presenting information. And as I said before, I think that for some organizations, this may be as much as they need to get really good, useful information out of their data. And so I strongly recommend that you take some time to explore with Tableau, either the paid desktop version or the public version, and see what you can do to get some really compelling and insightful visualizations out of your work in data science. For many people, their first experience of coding in data science is with the application SPSS. Now, I think of SPSS, and the first thing that comes to my mind is sort of life in the ivory tower, though this looks more like, Harry Potter. But if you think about it, the package name SPSS comes from Statistical Package for the Social Sciences, although if you ask IBM about it now, they'll act like it doesn't stand for anything. But it has its background in social science research, which is generally academic. And truthfully, I'm a social psychologist, and that's where I first learned how to use SPSS. But let's take a quick look at their webpage, ibm.com/SPSS. If you type that in, that'll just be a alias. It'll take you to IBM's main webpage. Now, IBM didn't create SPSS, but they bought it around version 16, and it was very briefly known as PASW, Predictive Analytics Software. That only lasted briefly, and now it's back to SPSS, which is where it's been for a long time. SPSS is a desktop program. It's pretty big. It does a lot of things. It's very powerful. It's used in a lot of academic research. It's also used in a lot of business consulting, management, and even some medical research. And the thing about SPSS is it looks like a spreadsheet, but it has drop-down menus to make your life a little bit easier compared to some of the programming languages that you can use. Now, you can get a free temporary version. If you're a student, you can get a cheap version. Otherwise, SPSS costs a lot of money. But if you have it one way or the other, when you open it up, this is what it's going to look like. I'm showing SPSS version 22. Now, it's currently on 24. And the thing about SPSS versioning is in any other software package, these would be point updates. So I sort of feel like we should be on 17.3 as opposed to 22 or 24, because the variations are so small that anything you learn from the earlier ones is going to work in the later ones. And there's a lot of backwards and forwards compatibility. So I'd almost say that this one, the version you have, practically doesn't matter. You get this little welcome splash screen, and if you don't want to see it anymore, you can get rid of it. I'm just going to hit cancel here. And this is our main interface. Looks a lot like a spreadsheet. The difference is you have a separate pane for looking at variable information, and then you have separate windows for output, and then an optional one for something called syntax. But let me show you how this works by first opening up a data set. SPSS has a lot of sample data sets in them, but they're not easy to get to, and they're really well hidden. On my Mac, for instance, let me go to where they are. In my Mac, I go to the Finder. I have to go Mac to Applications, to the folder IBM, to SPSS, to Statistics, to 22, the version number, to Samples. Then I have to say I want the ones that are in English, and then it brings them up. The .sav files are the actual data files. There are different kinds in here. So .sps is a different kind of file. And then we have a different one about planning analyses. So there are versions of it. I'm going to open up a file here called marketvalues.sav. It's a small data set in SPSS format. And if you don't have that, you can open up something else. It really doesn't matter for now. By the way, in case you haven't noticed, SPSS tends to be really, really slow when it opens. It also, despite being at version 24, tends to be kind of buggy and crashes. And so when you work with SPSS, you want to get in the habit of saving your work constantly and also being patient when it's time to open the program. So here's a data set that just shows addresses and house values and square feet for some information. This, I don't even know if this is real information. It looks artificial to me. But SPSS lets you do point and click analyses, which is unusual for a lot of things. So I'm going to come up here and I'm going to say, for instance, make a graph. I'm actually going to use what's called a legacy dialog to get a histogram of house prices. So I simply click values, put that right there, and I'll put a normal curve on top of it and hit OK. And then it's going to open up a new window, and it opened up a microscopic version of it here. So I'm going to make that bigger. This is the output window. And so this is a separate window, and it has a navigation pane here on the side. It tells me where the data came from, and it saves the command here. And then, there's my default histogram. And so we see most of the houses were right around $125,000, and then they went up to at least $400,000. I have a mean of 256,000, a standard deviation of about 80,000, and there's 94 houses in the data set. Fine, that's great. The other thing I can do is if I want to do some analyses, let me go back to the data just for a moment. For instance, I can come here to Analyze, and I can do descriptives. I'm actually going to do one here called Explore. And I'll take the purchase price and I'll put it right here. And I'm going to get a whole bunch of stuff just by default. I'm going to hit OK. And it goes back to the output window. Once again, made it tiny. And so now you see beneath my chart, I now have a table and I've got a bunch of information, a stem and leaf plot, and I've got a box plot too, a great way of checking for outliers. And so this is a really convenient way to save things. You can export this information as images. You can export the entire file as an HTML. You can do it as a PDF or a PowerPoint. There's a lot of options here, and you can customize everything that's on here. Now, I just want to show you one more thing that makes your life so much easier in SPSS. You see right here that it's putting down these commands. It's actually saying graph and then histogram normal equals value. And then down here, we've got this little command right here. Most people don't know how to save their work in SPSS, and they kind of just have to do it over again every time. But there's a very simple way to do this. What I'm going to do is I'm going to open up something called a syntax file. I'm going to go to New, Syntax. And this is just a blank window that's a programming window. It's for saving code. And let me go back to my analysis I did a moment ago. I'll go back to Analyze. I can still get at it right here. And Descriptives and Explore. And my information is still there. And what happens here is even though I set it up with drop-down menus and point and click, if I do this thing paste, then what it does is it takes the code that creates that command and it saves it to this syntax window. And this is just a text file. It saves it as .sps, but it's a text file that can be opened in anything. And what's beautiful about this is it's really easy to copy and paste, and you can even take this into like Word and do find and replace on it. And it's really easy to replicate the analyses. And so for me, SPSS is a good program, but until you use syntax, you don't know the true power of it, and it makes your life so much easier as a way of operating it. Anyhow, this is my extremely brief introduction to SPSS. All I want to say is that it's a very common program, kind of looks like a spreadsheet, but it gives you a lot more power and options, and you can use both drop-down menus and text-based syntax commands as well to automate your work and make it easier to replicate it in the future. I want to take a look at one more application for coding and data science that's called JASP. This is a new application, not very familiar to a lot of people and still in beta, but with amazing promise. You can basically think of it as a free version of SPSS. And you know what? We love free. But JASP is not just free, it's also open source, and it's intuitive, and it makes analyses replicable, and it even includes Bayesian approaches. And so take that all together, we're pretty happy and we're jumping for joy. So before we move on, you just may be asking yourself, JASP, what is that? Well, the creators emphatically deny that it stands for just another statistics program, but be that as it may, we'll just go ahead and call it JASP and use it very happily. You can get to it by going to jasp-stats.org, and let's take a look at that right now. JASP is a new program. They say a low-fat alternative to SPSS, but it is a really wonderful, great way of doing statistics. You're going to want to download it, specifying your platform. It even comes in Linux format, which is beautiful. And again, it's beta, so stay posted. Things are updating regularly. And if you're on Mac, you're going to need to use Xquartz, but that's an easy thing to install and makes a lot of things work better. And it's a wonderful way to do analyses. When you open up JASP, it's going to look like this. It's a pretty blank interface, but it's really easy to get going with it. So for instance, you can come over here to File, and you can even choose some example data sets. So for instance, here's one called Big Five. That's personality factors. And you've got data here that's really easy to work with. Let me scroll this over here for a moment. So there's our 5 variables. And let's do some quick analyses with these. Say, for instance, we want to get descriptives. We can pick a few variables. Now, if you're familiar with SPSS, the layout feels very much the same, and the output looks a lot the same. All I have to do is select what I want, and it immediately pops up over here. And then I can choose additional statistics. I can get quartiles, I can get the median, and you can choose plots. Let's get some plots. All I do is click on it and they show up. And that's a really beautiful thing. And you can modify these things a little bit. So for instance, I can take the plots and let's see if I can drag that down. And if I make it small enough, I can see the 5 plots. Well, I went a little too far on that one. Anyhow, you can do a lot of things here, and I can hide this. I can collapse that, and I can go on and do other analyses. Now, what's really neat though, is when you navigate away from it. So I just clicked in a blank area of the results pane. We're back to the data here. But if I click on one of these tables, like this one right here, it immediately brings up the commands that produced it. And I can just modify it some more if I want. Say I want skewness and kurtosis. Boom, they're in there. It's an amazing thing. And then I can come back out here. I can click away from that and I can come down to the plots, expand those. And if I click on that, it brings up the commands that made them. It's an amazingly easy and intuitive way to do things. Now, there's another really nice thing about JASP, and that is that you can share the information online really well through a program called osf.io. That stands for the Open Science Foundation. That's its web address, osf.io. So let's take a quick look at what that's like. Here's the Open Science Framework website, and it's a wonderful service. It's free, and it's designed to support open, transparent, accessible, accountable, collaborative research. And I really can't say enough nice things about it. What's neat about this is once you sign up for OSF, you can create your own area, and I've got one of my own. I'll go to that right now. So for instance, here's the Data Lab page in Open Science Framework. And what I've done is I created a version of this JASP analysis, and I've saved it here. In fact, let's open up my JASP analysis in JASP, and then I'll show you what it looks like in OSF. So let's first go back to JASP. And when we're here, we can come over to File and click Computer. And I just saved this file to the desktop. Click on Desktop. And you should have been able to download this with all the other files, DSO324JASP. I'm going to double click on that to open it. And now it's going to open up a new window. And you see I was working with the same data set, but I did a lot more analyses. I've got these graphs. I have correlation scatter plots. Come down here, I did a linear regression. And we just click on that and you can see the commands that produced it as well as the options. Didn't do anything special for that, but I did do some confidence intervals and specified that. And it's really a great way to work with all this. I'll click back in an empty area and you can see the commands go away. And so I've got my output here in JASP. When I saved it though, I had the option of saving it to OSF. In fact, if you go to this web page, osf.io/3t2jg, you'll actually be able to go to a page where you can see and download the analysis that I conducted. Let's take a look. This is that page. There's the address I just barely gave you. And what you see here is the same analysis that I conducted. It's all right here. So if you're collaborating with people, or if you want to show things to people, this is a wonderful way to do it. Everything's right there. Now this is a static image, but up at the top, people have the option of downloading the original file and working with it on their own. So in case you can't tell, I'm really enthusiastic about JASP and about its potential. Still in beta, still growing rapidly. I see it really as an open source, free and collaborative replacement to SPSS. And I think it's going to make data science work so much easier for so many people. I strongly recommend you give JASP a close look. Let's finish up our discussion of coding and data science, the applications part of it, by just briefly looking at some other software choices. And I'll have to admit, it gets kind of overwhelming because there are just so many choices. Now, this is in addition to the spreadsheets and Tableau and SPSS and JASP that we've already talked about. I mean, there's so much more than that. I'm going to give you a range of things that I'm aware of, and I'm sure I've left out some important ones or things that other people like really well. But these are some common choices and some less common but interesting ones. Number one, in terms of things that I did not mention, is SAS. SAS is an extremely common analytical program, very powerful, used for a lot of things. It's actually the first program that I learned. And on the other hand, it can be kind of hard to use and it can be expensive. But there's a couple of interesting alternatives. SAS also has something called the SAS University Edition. If you're a student, this is free and it's slightly, reduced in what it does. But the fact that it's free, and also it runs in a virtual machine, which makes it an enormous download, but it's a good way to learn SAS if it's something that you want to do. SAS also makes a program that I really love were it not so extraordinarily expensive, and that is called JUMP. And it's a visualization software. Think a little bit of like Tableau, how we saw it. You work with it visually, and this one you can drag things around. It's a really wonderful program. I personally find it prohibitively expensive. Another very common choice among working analysts is Stata, and some people use Minitab. Now, for mathematical people, there's MATLAB, and then of course there's Mathematica itself, but that's really more a language than a program. On the other hand, Wolfram, who makes Mathematica, is also the people who give us Wolfram Alpha. Most people don't think of this as a stats application because you can run it on your iPhone. But Wolfram Alpha is in fact incredibly capable. And especially if you pay for the pro account, you can do amazing things in this, including analyses, regression models, visualizations. And so it's worth taking a little closer look at that also, because it actually provides a lot of the data that you need. So Wolfram Alpha is an interesting one. Now, several applications that are more specifically geared towards data mining. So you don't want to do your regular, little t-tests and stuff on these, but there's RapidMiner, and there's Nime and Orange. And those are all really nice to use because they are control languages where you drag nodes onto a screen and you connect them with lines and you can see how things run through. All three of them are free or have free versions, and all three of them work in pretty similar manners. There's also BigML, which is for machine learning. And this is unusual because it's browser based. It runs on their servers. There's a free version, although you can't download a whole lot. It doesn't cost a lot to use BigML, and actually is a very friendly, very accessible program. Then in terms of programs you can actually install for free on your own computer, there's one called SOFA Statistics. That means Statistics Open for All. Kind of a cheesy title, but it's a good program. And then one with a web page straight out of 1990 is PAST3. This is paleontological software. On the other hand, does do very general stuff. It runs on many platforms, and it's a really powerful thing, and it's free, but it is relatively unknown. And then, speaking of relatively unknown, one that's near and dear to my heart is a web application called StatCrunch. It costs, but it costs like $6 or $12 a year. It's really cheap, and it's very good, especially for basic statistics and for learning. I used it in some of the classes that I was teaching. And then if you're deeply wedded to Excel and you just can't stand to leave that environment, you can purchase add-ins like Excel Stat, which give you a lot of statistical functions within the Excel environment itself. That's a lot of choices. And the most important thing here is don't get overwhelmed. There's a lot of choices, but you don't even have to try all of them. Really, the important question is what works best for you and the projects that you're working on. There's a few things you might want to consider in that regard. First off is functionality. Does it actually do what you want, or does it even run on your machine? You don't need everything that a program can do. I mean, think about all the stuff that Excel can do. People probably use 5% of what is available. Then there's also ease of use. Some of these programs are a lot easier to use than the others. And I personally find that the ones that are easy to use, I like them. And so you might say, no, I need to program because I need to do custom stuff. But I'm willing to bet that 95% of what people do does not require anything custom. Also, the existence of a community. Constantly when you're working, you come across problems, don't know how to solve it, and being able to simply get online and do a search for an answer and have enough of a community that there are people there who have put answers up and discuss these things. Those are wonderful. Some of these programs have very substantial communities. Some of them it's practically non-existent, and you get to decide how important that is to you. And then finally, of course, there's the issue of cost. Many of these programs I mentioned are free. Some of them are very cheap. Some of them run on sort of a freemium model, and some of them are outrageously expensive. So you don't buy them unless somebody else is paying for it. So these are some of the things that you want to keep in mind when you're trying to look at various programs. Also, let's mention this. Don't forget the 80-20 rule. You're going to be able to do most of the stuff that you need to do with only a small number of tools. 1 or 2, maybe 3 will probably be all that you ever need. So you don't need to explore the range of every possible tool. Find something that does what you need, find something you're comfortable with, and really try to extract as much value as you can out of that. So in sum, in our discussion of available applications for coding and data science, first, remember, applications are tools. They don't drive you, you use them. And that your goals are what drive the choice of your applications and the way that you do it. And the single most important thing is to remember what works for you may work well for somebody else. If you're not comfortable with it, if it's not the questions you address, then it's more important to think about what works for you and the projects that you're working on as you make your own choices for tools for working in data science. When you're coding in data science, one of the most important things you can do is be able to work with web data. And if you work with web data, you're going to be working with HTML. Now, in case you're not familiar with it, HTML is what makes the World Wide Web go round. What it stands for is Hypertext Markup Language. And if you've never dealt with web pages before, here's a little secret. Web pages are just text. It's just a text document, but it uses tags to define the structure of the document, and a web browser knows what those tags are and it displays them in the right way. So for instance, some of the tags, they look like this. They're in angle brackets, and you have angle bracket and then a beginning tag, so body. Then you have the body, the main part of your text, and then you have in angle brackets and a backslash body to let the computer know that you're done with that part. You also have P and backslash P for paragraphs. H1 is for header 1, and you put it in between that text. TD is for table data, or the cell in a table, and you mark it off that way. If you want to see what it looks like, just go to this document, DSO331html.txt. I'm going to go to that one right now. Now, depending on what text editor you open this up, it may actually give you the web preview. I've opened it up in TextMate, and so it actually is showing the text the way I typed it. I typed this manually, I just typed it all in there, and I have HTML to say what a document is. I have an empty header, but that sort of needs to be there. This I say what the body is, and then I have some text. LI is for list items. I have headers. This is for a link to a web page. Then I have a small table. And if you want to see what this looks like when it's actually displayed as a web page, we'll just go up here to Window and Show Web Preview. This is the same document, but now it's in a browser. And that's how you make a web page. Now, I know this is very fundamental stuff, but the reason this is important is because if you're going to be extracting data from the web, you have to understand how that information is encoded in the web and is going to be in HTML most of the time for a regular web page. Now, I will mention something that there's another thing called CSS, and web pages use CSS to define the appearance of a document. HTML is theoretically there to give the content, and CSS gives the appearance, and that stands for Cascading Style Sheets. I'm not going to worry about that right now because we're really interested in the content. And now you have the key to being able to read web pages and pull data from web pages for your data science projects. So, in sum, first, the web runs on HTML. That's what makes the web pages that are there. HTML defines the page structure and the content that's in the page. And you need to learn how to navigate the tags and the structure in order to get data from the web pages for your data science projects. The next step in coding in data science when you're working with web data is to understand a little bit about XML. I like to think of this as the part of web data that follows the imperative Data define thyself. XML stands for Extensible Markup Language. And what it is, XML is semi-structured data. What that means is that tags define data so a computer knows what a particular piece of information is. But unlike HTML, the tags are free to be defined any way you want. And so you have this enormous flexibility in there, but you're still able to specify it so the computer can read it. Now, there's a couple of places where you're going to see XML files. Number one is in web data. HTML defines the structure of a web page, but if they're feeding data into it, then that will often come in the form of an XML file. Interestingly, Microsoft Office files, if you have docx or XLSX, X part at the end stands for a version of XML that's used to create these documents. If you use iTunes, the library information that has all of your artists and your genres and your ratings and stuff, that's all stored in an XML file. And then finally, data files that often go with particular programs can be saved as XML as a way of representing the structure of the data to the program. And for XML, tags use opening and closing angle brackets just like HTML did. Again, the major difference is that you're free to define the tags however you want. So for instance, thinking about iTunes, you can define a tag that's genre, and you have the angle brackets and genre to begin that information, and then you have the angle brackets with the backslash to let it know you're done with that piece of information. Or you can do it for composer, or you can do it for rating, or you can do it for comments, and you can create any tags you want, and you put the information in between those two things. Now, let's take an example of how this works. I'm going to show you a quick data set that comes from the web. It's at airgast.com and API. This is a website that stores information about automobile Formula One racing. Let's go to this webpage and take a quick look at what it's like. So here we are at airgast.com, and it's the API for Formula One. And what I'm bringing up is the results of the 1957 season in Formula One racing. And here you can see who the competitors were in each race and how they finished and so on. So this is a data set that's being displayed in a web page. If you want to see what it looks like in XML, all you have to do is type XML onto the end of this .xml. I've done that already, so I'm just going to go to that one. You see, it's only this little bit that I've added, .xml. Now, it looks exactly the same because the web page is structuring XML data by default. But if you want to see what it looks like in its raw format, just do an option click on the web page and go to View Page Source. At least that's how it works in Chrome. And this is the structured XML page. And you can see we've got tags here. It says race name, circuit name, location. And obviously these are not standard HTML tags. They're defined for the purposes of this particular data set. But we begin with one, we have circuit name right there, and then we close it using the backslash right there. And so this is structured data. The computer knows how to read it, which is exactly, this is how it displays it by default. And so it's a really good way of displaying data, and it's a good way to know how to pull data from the web. You can actually use what's called an API, an application programming interface, to access this XML data, and it pulls it in along with its structure, which makes working with it really easy. What's even more interesting is how easy it is to take XML data and convert it between different formats because it's structured and the computer knows what you're dealing with. So for example one, it's really easy to convert XML to CSV or comma separated value files. That's the spreadsheet format because it knows exactly what the headings are and what piece of information goes in each column. Example 2, it's really easy to convert HTML documents to XML because you can think of HTML with its restricted set of tags as sort of a subset of the much freer XML. And 3, you can convert CSV or your spreadsheet comma separated value to XML and vice versa. You can bounce them all back and forth because the structure is made clear to the programs that you're working with. So in sum, here's what we can say. Number 1, XML is semi-structured data. What that means is it has tags to tell the computer what the piece of information is, but you can make the tags whatever you want them to be. And XML is very common for web data, and it's really easy to translate the formats, XML, HTML, CSV, so on and so forth, it's really easy to translate them back and forth, which gives you a lot of flexibility in manipulating data so you can get into the format you need for your own analysis. The last thing I want to mention about coding in data science and web data is something called JSON. And I like to think of it as a version of smaller is better. Now, what JSON stands for is JavaScript Object Notation, although JavaScript is supposed to be one word. And what it is that like XML, JSON is semi-structured data. That is, you have tags that define the data so the computer knows what each piece of information is. But like XML, the tags can vary freely. And so there's a lot in common between XML and JSON. So XML is a markup language. That's what the ML stands for. And that gives meaning to the text. It lets the computer know what each piece of information is. Also, XML allows you to make comments in the document, and it allows you to put metadata in the tags. You can actually put some information there in the angle brackets to provide additional context. JSON, on the other hand, is specifically designed for data interchange. And so it's got that special focus. And the structure of JSON corresponds with data structures. It directly represents objects and arrays and numbers and strings and booleans. And that works really well with the programs that you use to analyze data. Also, JSON is typically shorter than XML because it does not require the closing tags. Now, there are ways to do that with XML, but that's not typically how it's done. As a result of these differences, JSON is basically taking XML's place in web data. XML still exists, still used for a lot of things, but JSON is slowly replacing it. And we'll take a look at the comparison between the three by going back to the example we used in XML. This is data about Formula One car races in 1957 from airgast.com. And so you can just go to the first web page here, and then we'll navigate to the others from that. So this is the general page. This is if you just type in without the .xml or .json or anything. So it's a table of information about races in 1957. And we saw earlier that if you add just .xml to the end of this, it looks exactly the same. That's because this browser is displaying XML properly by default. But if you were to right click on it and go to view page source, you would get this instead. And you can see the structure. This is still XML. And so everything has an opening tag and a closing tag and some extra information in there. But if you type in .json, what you really get is this jumbled mess. Now, that's unfortunate because there is a lot of structure to this. So what I'm going to do is I'm actually going to copy all of this data. And then I'm going to go to a little web page. There's a lot of things you can do here. And it's a cute phrase. It's called JSON Pretty Print. And that is make it look structured so it's easier to read. I just paste that in there and hit Pretty Print JSON. And now you can see the hierarchical structure of the data. The interesting thing is that the JSON tags only have tags at the beginning. So it says series in quotes and then a colon. And then it gives the piece of information in quotes and a comma, and it moves on to the next one. And this is a lot more similar to the way that data would be represented in something like R or Python. And so it's also more compact. Again, there's things you can do with XML, but this is one of the reasons that JSON is generally becoming preferred as a data carrier for websites. And as you might have guessed, it's really easy to convert between the formats. It's easy to convert between XML, JSON, CSV, etc. And so you can get a web page where you just paste one version in and you get the other version out. There are some differences, but for the vast majority of situations, they're just kind of interchangeable. So in sum, what do we get from this? Like XML, JSON is semi-structured data where there are tags that say what the information is, but you can define the tags however you want. And JSON is specifically designed for data interchange. And because it reflects the structure of the data in the programs, that makes it really easy. And then also because it's relatively compact, JSON is replacing gradually XML on the web as a container for data on web pages. If we're going to talk about coding in data science and the languages that are used, then first and foremost is R. The reason for that is, according to many standards, R is the language of data and data science. For example, take a look at this chart. This is a ranking based on a survey of data mining experts of the software that they use in doing their work. And R is right there at the top. R is first. And in fact, that's important because there's Python, which is usually taken hand in hand with R for data science, but R sees 50% more use than Python does, at least in this particular list. Now, there's a few reasons for that popularity. Number one, R is free and it's open source, both of which make things very easy. Second, R is specially developed for vector operations. That means it's able to go through an entire list of data without having to write for loops to go through it. If you've ever had to write for loops, then you know that that would be kind of disastrous having to do that with data analysis. Next, R has a fabulous community behind it. It's very easy to get help on things with R. You Google it, you're going to end up in a place where you're going to be able to find good examples of what you need. And probably most importantly, R is very capable on its own, but there are 7,000 packages, actually it's many more than that, 7,000 packages that add capabilities to R. Essentially, it can do anything. Now, when you're working with R, you actually have a choice of interfaces. That is, how do you actually do the coding and how do you get your results? R comes with its own IDE or interactive development environment. You can do that, or if you're on a Mac or a Linux, you can actually do R through the terminal, through command line. If you've installed R, you just type R and it starts up. There's also a very popular development environment called RStudio, and that's actually the one that I use and I'll be using for all of my examples. But another new competitor is Jupyter, which is very commonly used for Python. It's what I use for examples there. It works in a browser window, even though it's locally installed. And RStudio and Jupyter, there's pluses and minuses to each one of them. I'll mention them as we get to them. But no matter what interface you use, R's command line, you are typing lines of code in order to get the commands. Some people get really scared about that, but really there's some advantages to that in terms of the replicability and really the accessibility, the transparency of your commands. So for instance, here's a short example of some commands in R. You can enter them into what's called the console, and that's just like one line at a time. That's called an interactive way. Or you can save scripts and run bits and pieces of them selectively. That makes your life a lot easier. No matter how you do it, if you're familiar with programming in other languages, then you're going to find that R is a little weird. It has an idiosyncratic model. It makes sense once you get used to it, but it is a different approach. And so it does take some adaptation if you're accustomed to programming in other languages. Now, once you do your programming and get your output, what you're going to get is graphs in a separate window. You're going to get text and numbers, numerical output in the console. And no matter what you get, you can save the output to files. So that makes it portable. You can do it in other environments. But most importantly, I like to think of this. Here's our box of chocolates where you never know what you're going to get. The beauty of R is in the packages that are available to expand its capabilities. Now, there are two sources of packages for R. One goes by the name of CRAN, and that stands for the Comprehensive R Archive Network. And that's at cran.rstudio.com. And what that does is it takes these 7,000 or so different packages that are available, and it organizes them in topics that they call task views. And for each one, if they've done their homework, you have data sets that come along with that package. You have a manual in PDF format, and you can even have vignettes where they run through examples of how to do it. Another interface is called Crantastic, and the exclamation point is part of the title. That's at crantastic.org. And what this is an alternative interface that links to CRAN. So if you find something like in Crantastic and you click on the link, it's going to open in CRAN. But the nice thing about Crantastic is it shows the popularity of packages, and it also shows how recently they were updated. And that can be a nice way of knowing that you're getting sort of the latest and greatest. Now, from this very abstract presentation, we can say a few things about R. Number one, according to many, R is the language of data science. And it's a command line interface. You're typing lines of code. So that gives it both a strength and it's a challenge for some people. But the beautiful thing is the thousands and thousands of packages of additional code and capability that are available for R that make it possible to do nearly anything in this statistical programming language. When talking about coding in data science and the languages, along with R, we need to talk about Python. Now, Python, the snakes, is a general purpose program that can do it all, and that's its beauty. If we go back to this survey of the software used by data mining experts, you see that Python's there. It's number 3 on the list. And what's significant about that is on this list, Python is the only general purpose programming language. It's the only one that can theoretically be used to develop any kind of application that you want. That gives it some special power compared to all these others, most of which are very specific to data science work. So the nice things about Python are, number one, it's general purpose. It's also really easy to use. And if you have a Macintosh or a Linux computer, Python is built into it. Also, Python has a fabulous community around it with hundreds of thousands of people involved. And also, Python has thousands of packages. Now, it actually has something like 70 or 80,000 packages, but in terms of ones that are specific to data, there are still thousands available that give it some incredible capabilities. Now, a couple of things to know about Python. First is about versions. There are 2 versions of Python that are in wide circulation. There's 2.x, so that means like 2.5, 2.6, and there's 3.x, 3.1, 3.2. Version 2 and version 3 are similar, but they're not identical. And in fact, the problem is this. There are some compatibility issues where code that runs in one does not run in the other. And consequently, most people have to choose between one or the other. And what this leads to is that many people still use 2.x. I have to admit, the examples that I use, I'm using 2.x because so many of the data science packages are developed with that in mind. Now, let me say a few things about interfaces for Python. First, Python does come with its own interactive development and learning environment. They call it idle. You can also run it from the terminal or command line interface or any IDE that you have. Now, a very common and very good choice is Jupyter. Jupyter is a browser-based framework for programming, and it was originally called IPython, and that served as its initial version. So a lot of times when people talk about IPython, what they're really talking about is Python in Jupyter, and the two are sometimes used interchangeably. One of the neat things you can do is there are 2 companies, there's Continuum and Endthought, both of which have made special distributions of Python with hundreds and hundreds of packages pre-configured to make it very easy to work with data. I personally prefer Continuum Anaconda. It's the one that I use. A lot of other people use it, but either one's going to work and it's going to get you up and running. And like I said with R, no matter what interface you use, all of them are command line. You're typing lines of code. Again, there are some tremendous strengths to that, but it can be intimidating to some people at first. In terms of the actual commands of Python, you have some examples here on the side. The important thing to remember is that it's a text interface. On the other hand, Python is familiar to millions of coders because it's very often a first programming language that people learn to do general purpose programming. And there are a lot of very simple adaptations for data that make it very powerful for data science work. So let me say something else again. Data science loves Jupyter, and Jupyter is the browser-based framework. It's a local installation, but you access it through a web browser that makes it possible to really do some excellent work in data science. There's a few reasons for this. When you're working in Jupyter, you get text output, and you can use what's called Markdown as a way of formatting documents. You can get inline graphics where the graphics just show up directly beneath the code that you did it. Also, it's really easy to organize and present and to share analyses that are done in Jupyter, which makes it a strong contender for your choices in how you do data science programming. Another one of the beautiful things about Python, like R, is that there are thousands of packages available. In Python, there's one main repository. It goes by the name PyPy, which is for the Python Package Index. Right here it says there's over 80,000 packages, and 7 or 8,000 of those are for data specific purposes. Now, some of the packages that you'll get to be very familiar with are NumPy and SciPy, which are for scientific computing in general. Matplotlib and a development of it called Seaborn are for data visualization and graphics. Pandas is the main package for doing statistical analysis. And for machine learning, almost nothing beats scikit-learn. And when I go through hands-on examples in Python, I will be using all of these as a way of demonstrating the power of the program for working with data. So, in sum, we can say a few things. Number one, Python is a very popular program, familiar to millions of people, and that makes it a good choice. Second, of all the languages we use for data science on a frequent basis, this is the only one that's general purpose, which means it can be used for a lot of things other than processing data. And it gets its power, like R does, from having thousands of contributed packages, which greatly expand its capabilities, especially in terms of doing data science work. A choice for coding in data science, one of the languages that may not come immediately to mind when they think data science, is SQL or SQL. And SQL is the language of databases. And we think, why do we want to work in SQL? Well, to paraphrase the famous bank robber Willie Sutton, who apparently explained why he robbed banks and said, because that's where the money is. The reason we would work with SQL in data science is because that's where the data is. And so let's take another look at our ranking of software among data mining professionals. And there's SQL. It's third on the list. And also, of this list, it's the first database tool. Other tools in there, for instance, get much fancier and they're much newer and shinier, but SQL's been around for a while and is very, very capable. Now, there's a few things to know about SQL. By the way, you'll notice I'm saying SQL, even though that stands for something. That stands for Structured Query Language. SQL is a language. It's not an application. There's not a program SQL. It's a language that can be used in different applications. Primarily, SQL is designed for what are called relational databases. And those are special ways of storing structured data that you can pull in, you can put things together, you can join them in special ways, you can get some summary statistics. And then what you usually do is you then export that data into your analytical application of choice. So the big word here is RDBMS. And that stands for Relational Database Management System. And that's where you will usually see SQL as a query language being used. In terms of relational database management systems, there are a few very common choices. In the industrial world where people have some money to spend, there's Oracle database is a very common one, and Microsoft SQL or SQL Server. In the open source world, two very common choices are MySQL. Even though we generally say SQL, when it's here, you generally say MySQL. And then another one is PostgreSQL. These are both open source free versions of the language. They're sort of dialects of each that make it possible for you to be working with databases and get your data out. The neat thing about them, no matter what you do, is that databases minimize data redundancy by using connected tables. Each table has rows and columns, and they store different levels or different of abstraction or measurement, which mean you only have to put the information in one place and then it can refer to lots of other tables. Makes it very easy to keep things organized and up to date. When you're looking at a way of working with a relational database management system, you get to choose in part between using a graphical user interface or GUI, and some of those include SQL Developer and SQL Server Management Studio, two very common choices. And there are a lot of other ones like Toad and some other choices that are graphical interfaces for working with these databases. And there are also text-based interfaces. So really any command line interface and any interactive development environment or programming tool is going to be able to do that. Now you can think of yourself being on the command deck of your ship and learn a few basic commands that are very important for working with SQL. There are just a handful of commands that can get you most of where you need to go. There is the select command where you're choosing the cases that you want to include. From says which tables are you going to be extracting them from. Where is a way of specifying conditions, and then order by, obviously, is just a way of putting it all together. This works because usually when you're in a SQL database, you're just pulling out the information. You want to select it, you want to organize it, and then what you're going to do is you're going to send the data to your program of choice for further analysis, like R or Python or whatever. So in sum, here's what we can say about SQL. Number one, as a language, it's generally associated with relational databases, which are very efficient and well-structured ways of storing data. Just a handful of basic commands can be extremely useful when working with databases. You don't have to be a super ninja expert. Really, a handful, 5-10 commands will probably get you everything you need out of a SQL database. And then once you get the data organized, it's typically exported to some other program for analysis. When you talk about coding in any field, one of the languages or one of the groups of languages that come up most often are C, C++, and Java. Now, these are extremely powerful applications and very frequently used for sort of professional production level coding. In data science, the place where you're going to see these languages most often is in the bedrock, the absolute fundamental layer that makes the rest of data science possible. So for instance, C and C++. C is from the 60s, C++ is from the 80s, and they have extraordinarily wide usage. And their major advantage is that they're really, really fast. In fact, C is usually used as the benchmark for how fast is a language. They're also very, very stable, which makes them really well suited to production level code and, for instance, server use. What's really neat is that in certain situations, if time is really important, if speed's important, then you can actually use C code in R or other statistical languages. Next is Java. Java is based on C++. Its major contribution was the WARA, or write once, run anywhere. The idea that you're going to be able to develop code that is portable to different machines and different environments. And because of that, Java is actually the most popular computer programming language overall against all tech situations. And the place where you would use these in data science is, like I said, when time is of the essence, when something has to be fast, it has to get the job accomplished quickly, and it has to not break, then these are the ones that you're probably going to use. The people who are going to use it are primarily going to be engineers. So the engineers and the developers, the software developers who deal with the inner workings of the algorithms in data science, or the back end of data science, the servers and the mainframes and the entire structure that makes analysis possible. In terms of analysts, people who are actually analyzing the data typically don't do hands-on work with the foundational elements. They don't usually touch C or C++. More the work is on the front end or closer to the high-level languages like R or Python. In sum, C, C++, and Java form a foundational bedrock and the back end of data and data science. And they do this because they're very fast and they are very reliable. On the other hand, given their nature, that work is typically reserved for the engineers who are working with the equipment that runs in the back that makes the rest of the analysis possible. I want to finish our extremely brief discussion of coding in data sciences and the languages that can be used by mentioning one other that's called Bash. And Bash really is a great example of old tools that have survived and are still being used actively and productively with new data. You can think of it this way. It's almost like typing on your typewriter. You're working at the command line. You're typing out code through a command line interface, or CLI. Now, this method of interacting with computers practically goes back to the typewriter phase because it predates monitors. So before you even had a monitor, you would type in the code and it would print it out on a piece of paper. And the important thing to know about the command line is it's simply a method of interacting. It's not a language because lots of different languages can run at the command line. So for instance, it's important to talk about the concept of a shell. Now in computer science, a shell is a language or something that wraps around the computer. It's a shell around the language that is the interaction level for the user to get things done at the lower levels that aren't really human friendly. On Mac computers and Linux, the most common is Bash, which is short for Born Again Shell. On Windows computers, the most common version is PowerShell. But whatever you do, there actually are a lot of choices. There's the Bourne shell, there's the C shell, which is why I have a C shell right here. The Z shell, there's Fish for friendly interactive shell, and a whole bunch of other choices. But Bash is the most common on Mac and Linux, and PowerShell is the most common on Windows as a method of interacting with the computer at the command line level. Now there's a few things you need to know about this. First, you have a prompt of some kind. In Bash, it's a $sign, and that just means type your command here. Then the other thing is you type one line at a time. It's actually amazing how much you can get done with what's called a one-liner program by sort of piping things together so one feeds into the other. You can run more complex commands if you use a script. And so you call a text document that has a bunch of things in it, and you can get much more elaborate analyses done. Now we have our tools here. In Bash, we talk about utilities. And what these are specific programs that accomplish specific tools. Bash really thrives on do one thing and do it very well. There are two general categories of utilities for Bash. Number one is the built-ins. These are the ones that come installed with it, and so you're able to use them at any time by simply calling in their name. Some of the most common ones are cat, which is for catenate, and that's to put information together. There's awk, which is its own interpreted programming language, but it's often used for text processing from the command line. By the way, the name awk comes from the initials of the people who created it. Then there's grep, which is for global search with a regular expression, and print. It's a way of searching for information. And then there's sed, which stands for stream editor, and its main use is to transform text. You can do an enormous amount with just these four utilities. A few more are head and tail that display the first or last 10 lines of a document, sort and unique, which sort and count the number of unique answers in a document, WC, which is for word count, and printf, which formats the output that you get in your console. And while you can get a huge amount of work done with just this small number of built-in utilities, there are also a wide range of installables or other command line utilities that you can add to Bash or to whatever program you're using. So for instance, some really good ones that have been recently developed are JQ, which is for pulling in JSON or JavaScript object notation data from the web. And then there's JSON to CSV, which is a way of converting JSON to CSV format, which is what a lot of statistical programs are going to be happier with. There's Rio, which allows you to run a wide range of commands from the statistical programming language R in the command line as part of Bash. And then there's BigMLer, and this is a command line tool that allows you to access BigML's machine learning servers through the command line. Normally you do it through a web browser and it accesses their servers remote. It's an amazingly useful program, but to be able to just pull it up when you're in the command line is an enormous benefit. What's interesting is that even though you have all these opportunities, all these different utilities, you can do amazing things, and that there still is active development of utilities for the command line. So let's say this, in sum, despite being in one sense as old as the dinosaurs, the command line survives because it is extremely well evolved and well suited to its purpose of working with data. The utilities, both the built-in and the installables, are fast and they are easy. And generally they do one thing and they do it very, very well. And then surprisingly, there is an enormous amount of very active development of command line utilities for these purposes, especially with data science. One critical task when you're coding in data science is to be able to find the things that you're looking for. And regex, which is short for regular expressions, is a wonderful way to do that. You can think of it as the supercharged method for finding needles in haystacks. Now, regex tends to look a little cryptic. So for instance, here's an example of something that's designed to determine whether something is a valid email address. And it specifies what can go in the beginning. You have the @ sign in the middle. Then you've got a certain number of numbers and letters, and then you have to have a dot something at the end. And so this is a special kind of code for indicating what can go where. Now, regular expressions, or regex, are really a form of pattern matching in text. And it's a way of specifying exactly what needs to be where, what can vary, and how much it can vary. And you can write both specific patterns, say I only want a 1-letter variation here, or very general, like the email validator that I showed you. And the idea here is you can write this search pattern, your little wildcard thing. You can find the data, and then once you identify those cases, then you can export them into another program for analysis. So here's a short example of how it can work. What I've done is I've taken some text documents. They're actually the text to Emma and to Pygmalion, 2 books I got off of Project Gutenberg. And this is the command, grep::l.ve ***.txt. So what I'm looking for are lines in either of these books that start with L. Then they have one character, can be whatever, and then that's followed by VE. And then the .txt means search for all of the text files in that particular folder. And what it found is lines that began with love and lived and lovely and so on. Now, in terms of the actual nuts and bolts of regular expressions, there are some certain elements. There are literals, and those are things that mean exactly what they are. You type the letter L, you're looking for the letter L. There are also meta characters, which specify, for instance, things needs to go here. They're characters, but they actually really code that give representations. There are also escape sequences, which are something that you use to say, well, normally this character is used as a variable, but I actually want to really look for a period as opposed to a placeholder. Then you have the entire search expression that you create, and then you have the target string, the thing that it's searching through. So let me give a few very short examples. This is the caret. It's sometimes called a hat, or in French, a circonflexe. And what that means is you're looking for something that's at the beginning of the text that you're searching. So for example, you can have caret and capital M. That means you need something that begins with a capital M. So for instance, the word Mac, true, it will find that. But if you have iMac, there's a capital M, but it's not the first thing. So that'll be false. It won't find that. The $sign means you're looking for something that is at the end of the string. So for example, ing and then $sign, that'll find the word fling because it ends with ing, but it won't find the word flings because it actually ends with an S. And then the dot, the period, simply means we're looking for one letter, and it can be anything. So for example, you can write AT period, and that will find data because it has an A, a T, and then one letter after it. But it won't find flat because flat doesn't have anything after the AT. And so these are extremely simple examples of how it can work. Obviously, it gets more complicated, and the real power is when you start combining these bits and elements. Now, one interesting thing about this is you can actually treat this as a game. I love this website. It's called regex golf, and it's at regex.alf.nu. And what it does is it brings up lists of words, 2 columns, and your job is to write a regular expression in the top that matches all the words on the left column and none of the words on the right, and that uses the fewest characters possible. And you get a score. And it's a great way of learning how to do regular expressions and learning how to search in a way that's going to get you the data that you need for your projects. So, in sum, regex or regular expressions help you find the right data for your project. They're very powerful and they're very flexible. Now, on the other hand, they are cryptic, at least when you first look at them. But at the same time, it's like a puzzle, and it can be a lot of fun if you practice it and you see how you can find what you need. I want to thank you for joining me in coding and data science, and we'll wrap up this course by talking about some of the specific next steps that you can take for working in data science. The idea here is that you want to get some tools and you want to start working with those tools. Now, please keep in mind something that I've said at another time. Data tools and data science are related. They're important, but don't make the mistake of thinking that if you know the tools that you have done the same thing as actually conducted data science. That's not true. People sometimes get a little enthusiastic and they get a little carried away. What you need to remember is the relationship really is this. Data tools are an important part of data science, but data science itself is much bigger than just the tools. Now, speaking of tools, remember there's a few kinds that you can use and that you might want to get some experience with these. Number one, in terms of apps or just specific built applications, Excel and Tableau are really fundamental for both getting the data from clients or doing some basic data browsing. And Tableau is really wonderful for interactive data visualization. I strongly recommend that you get very comfortable with both of those. In terms of code, it's a good idea to learn either R or Python, or ideally to learn both because you can use them hand in hand. In terms of utilities, it's a great idea to learn how to work with Bash, the command line utility, and to use regular expressions or regex. You can actually use those in lots and lots of programs, regular expressions. And so they can have a very wide application. And then finally, data science requires some kind of domain expertise. You're going to need some sort of field experience or intimate understanding of a particular domain and the challenges that come up and what constitutes workable answers and the kind of data that's available. Now, as you go through all of this, you don't need to build this monstrous list of things. Remember, you don't need everything. You don't need every tool. You don't need every function. You don't need every approach. Instead, remember, get what's best for your needs and for your style. But no matter what you do, remember, tools are tools. They're a means to an end. Instead, you want to focus on the goal of your data science project, whatever it is. And I can tell you really, the goal is meaning, extracting meaning out of your data to make informed choices. In fact, I'll say a little more. The goal is always meaning. And so with that, I strongly encourage you, get some tools, get started in data science, and start finding meaning in the data that's around you. Welcome to Mathematics and Data Science. I'm Barton Poulson, and we're going to talk about how mathematics matters for data science. Now, you may be saying to yourself, why math? And computers can do it. I don't need to do it. And really, fundamentally, I don't need math. I'm just here to do my work. Well, I'm here to tell you, no, you need math. That is, if you want to be a data scientist, and I assume that you do. So we're going to talk about some of the basic elements of mathematics, really at a conceptual level, and how they apply to data science. There are a few ways that math really matters to data science. Number one, it allows you to know which procedures to use and why, so you can answer your questions in a way that's the most informative and most useful. Two, if you have a good understanding of math, then you know what to do when things don't work right, that you get impossible values or things won't compute, and that makes a huge difference. And then three, an interesting thing is that some mathematical procedures are easier and quicker to do by hand than by actually firing up the computer. And so for all three of these reasons, it's helpful to have at least a grounding in mathematics if you're going to do work in data science. Now, probably the most important thing to start with is algebra. And there are three kinds of algebra that we want to mention. The first is elementary algebra. That's the regular x plus y. Then there's linear or matrix algebra, which looks more complex, but is conceptually simpler and is used by computers to actually do the calculations. And then finally, I'm going to mention systems of linear equations where you have multiple equations simultaneously that you're trying to solve. Now, there's more math than just algebra. A few other things that I'm going to cover in this course. A little bit of calculus, a little bit of big O or order, which has to do with the speed or the complexity of operations. A little bit of probability theory, and a little bit of Bayes or Bayes' theorem, which is used for getting posterior probabilities and changes the way that you interpret the results of an analysis. And for the purposes of this course, I'm going to demonstrate the procedures by hand. Of course, you would use software to do this in the real world, but we're dealing with simple problems at conceptual levels. And really the most important thing to remember is, even though a lot of people get put off by math, really you can do it. And so in sum, let's say these three things about math. First off, you do need some math to do good data science. It helps you diagnose problems. It helps you choose the right procedures. And interestingly, you can do a lot of it by hand, or you can use software, computers to do the calculations as well. As we begin our discussion of the role of mathematics in data science, we'll of course begin with the foundational elements. And in data science, nothing is more foundational than elementary algebra. Now, I'd like to begin this with really just a little bit of history. In case you're not aware, the first book on algebra was written in 820 by Muhammad ibn Musa al-Khwarizmi, and it was called The Compendious Book on Calculation by Completion and Balancing. Actually, it was called this, which if you transliterate that comes out to this, but look at this word right here. That's the algebra, which means restoration. Any case, that's where it comes from. And for our concerns, there are several kinds of algebra that we're going to talk about. There's elementary algebra, there's linear algebra, and there are systems of linear equations. We'll talk about each of those in different videos. But to put it into context, let's take an example here of salaries. Now, this is actually based on real data from a survey of the salary of people employed in data science. And to give a simple version of it, the salary was equal to a constant. That's sort of an average value that everybody started with. And to that, you added years, and then you added some measure of bargaining skills and how many hours they worked per week. And that gave you a prediction, but because it wasn't exact, there's also some error to throw into it to get to the precise value that each person has. Now, if you want to abbreviate this, you can write it kind of like this: S plus C plus Y plus B plus H plus E. Although it's more common to write it symbolically like this. And let's go through this equation very quickly. The first thing we have is outcome. We call that Y, the variable Y, for person I. I stands for each case in our observations. So here's outcome Y for person I. This letter right here is a Greek beta, and it represents the intercept or the average. That's why it has a 0, because we don't multiply it times anything. But right next to it, we have the coefficient for variable 1. So beta, which means a coefficient, sub 1 for the first variable. And then we have variable 1, and then x1 means variable 1, and then the I means it's the score on that variable for person I, whoever we're talking about. And then we do the same thing for variables 2 and 3, and then at the end, we have little epsilon here with an I for the error term for person I, which says how far off the prediction was from their actual score. Now I'm going to run through some of these procedures and we'll see how they can be applied to data science. But for right now, let's just say this in sum. First off, algebra is vital to data science. It allows you to combine multiple scores, get a single outcome, do a lot of other manipulations. And really, the calculations are easy for one case at a time, especially when you're doing it by hand. The next step in mathematics for data science foundations is to look at linear algebra, or an extension of elementary algebra. And depending on your background, you may know this by another name, and I like to think, welcome to the matrix, because it's also known as matrix algebra, because we're dealing with matrices. Now, let's go back to an example I gave in the last video about salary, where salary is equal to a constant plus years plus bargaining plus hours plus error. Okay, that's a way to write it out in words. And if you want to put it in symbolic form, it's going to look like this. Now, before we get started with matrix algebra, we need to talk about a few new words. Maybe you're familiar with them already. The first is scalar, and this means a single number. And then a vector is a single row or a single column of numbers that can be treated as like a collection. That usually means a variable. And then finally, a matrix consists of many rows and columns, sort of a big rectangle of numbers. The plural of that, by the way, is matrices. And the thing to remember is that machines love matrices. Now, let's take a look at a very simple example of this. Here is a very basic representation of matrix algebra or linear algebra, where we're showing data on 2 people on 4 variables. So over here on the left, we have the outcomes for cases 1 and 2, our people 1 and 2. and you put them in the square brackets to indicate that it's a vector or a matrix. Here on the far left, it's a vector because it's a single column of values. Next to that is a matrix that has here on the top the scores for case 1, which I've written as x's. x1 is for variable 1, x2 is for variable 2, and the second subscript is to indicate that it's for person 1. Below that are the scores for case 2, the second person. And then over here in another vertical column are the regression coefficients. That's a beta there that we're using. And then finally, we've got a tiny little vector here at the end, which contains the error terms for cases 1 and 2. Now, even though you would not do this by hand, it's kind of helpful to run through the procedure. So I'm going to show it to you by hand. And we're going to take 2 fictional people. This will be fictional person number 1. We'll call her Sophie. We'll say that she's 28 years old, and we'll say that she has good bargaining skills, a 4 on a scale of 5, and that she works 50 hours a week, and that her salary is $118,000. Our second fictional person, we'll call him Lars, and we'll say that he's 34 years old, and that he has moderate bargaining skills, 3 out of 5, works 35 hours per week, and has a salary of $84,000. And so if we're trying to look at salaries, we can go back to our matrix representation that we had here with our variables indicated with their Latin and sometimes Greek symbols. And we're going to replace those variables with actual numbers so we can get the salary for Sophie, our first person. So let me plug in the numbers here. And let's start with the result here. Sophie's salary is $118,000. And here's how these numbers all add up to get that. The first thing here is the intercept, and we just multiply that times 1. So that's sort of the starting point. And then we get this number 10, which actually has to do with years over 18. She's 28, so that's 10 years over 18. We multiply each year by 1395. Next is bargaining skill. She's got a 4 out of 5, and for each step up, you get $5,900. By the way, these are real coefficients from study of survey of salary of data scientists. And then finally, hours per week. For each hour, you get $382. Now, we can add those up and we can get a predicted value for her, but it's a little low. It's 30,000 low, which you may say, well, that's really messed up. Well, that's because there's like 40 variables in the equation, including she might be the owner. And if she's the owner, yeah, she's going to make a lot more. And then we do a similar thing for the second case. But what's neat about matrix algebra or linear algebra is that you can use matrix notation. And this means the same stuff. And what we have here are these bolded variables that stand in for entire vectors or matrices. So for instance, this Y, a bold Y, stands for the vector of outcome scores. This bolded X is the entire matrix of values that each person has on each variable. This bolded beta is all of the regression coefficients. And then this bolded epsilon is the entire vector of error terms. And so it's really super compact way of representing the entire collection of data and coefficients that you use in predicting values. So in sum, let's say this. First off, computers use matrices. They like to do linear algebra to solve problems. And it's conceptually simpler because you can put it all there in this tight formation. In fact, it's a very compact notation and it allows you to manipulate entire collections of numbers pretty easily. And that's the major benefit of learning a little bit about linear or matrix algebra.